So after 2 setup lessons, we're finally ready for this method called integration by trig substitution. This is definitely the most, I suppose it's the most complex of the methods, but it encompasses a wide variety of problems we can deal with. So the first question is, when do we use trigonometric substitution? And the answer is that there are sort of 3 different cases, and they all have to do with a very specific type of binomial, right? So if you're ever working with sort of like if you're ever working with a sum or difference of squares. So if you ever have a constant squared minus x squared, or if you ever have x squared minus a constant squared, or if you ever have, x squared plus a constant squared. And the variable could even have, a constant stuck to it as well. But the idea is if you have any integral that you don't know how to do any other way, and I should preface with that. If you've got another way to go through the problem, great, do it. But if you're looking at a problem and you're just, I can't find anything that's going to make this work, then integration by trigonometric substitution might be the way to go if the core part of the problem looks like one of these things. Specifically, if there are effectively 2 squared things, one of them being a variable and one of them being a constant. Okay, and the way that we're going to do these problems is basically by using the tricks and the methods that we just practiced in the last 2 videos and sort of putting them all together. These are fascinating problems. They're near and dear to my heart because it was something that I sort of found when I was in school, and it was really neat for me. So sorry I'm kind of crazy about them, but these are really neat problems. So get your thinking cap on. We've got good work to do. So our strategy is this, and I tried to color code this to make it as nice as possible. Step 1 is you have to choose the appropriate substitution, right? If the expression is constant minus variable, then you're going to do a sine substitution. If it's constant plus variable, then it's a tangent substitution. And if it's variable minus constant, then it's a secant substitution. And this sort of harkens back to the first video we did, where I sort of mentioned, hey, this structure feels like arcsine. This structure feels like arctangent. This structure feels like arcsecant. The other thing you'll notice is that there's this a over b thing in front. The reason that we need that, I want you to sort of think about it. When you plug this thing in, I'm going to need that b squared to basically turn into an a squared so I can factor it out. That's why whatever's in front of x, that b, goes on the bottom. So that when this thing gets squared, you've got b squared on the bottom. In all 3 cases, b squared on the bottom, which will cancel out with that b squared, leaving you with just an a squared in those positions. So, long story short, step 1, choose the appropriate substitution. Choose the right thing for these. Step 2, for that substitution, compute what dx is going to be, right? Because when we do a substitution, we need to know what dx is, right? For step 3, you're going to do that substitution. You're actually going to perform the substitution and simplify very carefully, which was basically what we did in the second video. The first video was us doing the substitution, simplifying things down. Then the 4th step is, okay, now that you've done that substitution, integrate what's left. And then the 5th step is after you've integrated, change the variable back into x using the method we did in the second video. So that's our strategy. That's how we're going to do these problems. I've got a couple of examples, so let's go at them. Okay, so for this example, we're gonna try this method. Notice that we have a squared thing and another squared thing together inside of a root. I don't see any other way we're going to get through this problem. So trigonometric substitution is sort of going to be what we're going to try. I'd like you guys to try the first step on your own. The first step is to identify, so what type of substitution do I need to use here? So pause the video, at least write down what your substitution is going to be, and then sort of check back in with the video to make sure you got the right one. So because it's a variable squared minus a constant squared, it's going to be a secant style substitution, and so I'm going to write x equals 2/3 secant u, right? Remember, the 3 is going on the bottom because when I square it, I want the bottom to have a 9 so that it'll cancel with the 9 that's there. The 2 is going on the top so that when I square it, I get a 4, and that 4 matches the one that's here. Okay. Now, in our strategy, what's the next step after choosing that substitution? Right? after that we're supposed to compute what our dx is, because I'm about to do an integral, right? My dx will be 2/3 secant u tangent u du. Okay? Once you have those two things, your next step is to substitute those things in and simplify the resulting integral. So this is something I want you guys to try on your own, but a recommendation that I would make, I think it's worth your time to potentially, especially when these problems get more complicated, you might want to first just do the 9x squared minus 4 part, like just figure out what that is, then bring all the components back to this thing. So pause the video, do that, do the full u substitution, and check back in before you start doing the integral. So first I'm going to do 9x squared minus 4. Right, if I plug my 2/3 secant u in, I'm going to end up with 9 times 4/9 secant squared u minus 4. That's 4 secant squared u minus 4. If I factor out the 4, I'll be left with secant squared minus 1, which is tangent squared. So I get 4 tangent squared u. So this thing will replace the 9x squared minus 4. So now to replace everything else, right? I have the integral of the square root, and we said this was going to turn into 4 tangent squared u. Then, in the denominator I have x. Well, x, our original substitution we chose to be 2/3 secant u. And then we have times our dx. The dx on the end is this dx that I actually computed, right? It's 2/3 secant u tangent u du. Okay, so this is what you have, this thing is what you have after doing this u substitution. And I'll admit, this looks horrible. But the good news is, magic happens. Like, this always works nicely for these problems, right? So I'm now going to ask you guys, if you haven't already done so, pause the video and simplify this. You should notice a lot of nice things happen. First thing I notice is that there's a 2/3 on the top and a 2/3 on the bottom, so these two things, will divide out to be 1. The next thing I notice is that there's a secant u and there's a secant u. There's one on the top and one on the bottom. Those will also divide out to 1. Right? The next thing I notice is that I have the square root of 4 tangent squared. That 4 tangent squared can just become 2 tangent u. And then finally there's another tangent u and a du, so this is just tangent squared du. So this entire crazy problem, by using this substitution, has dropped down to just this. Now the question is, can we do that integral? Have we learned how to deal with an even power of tangent? I believe that we have. Right, with tangent squared, with an even power of tangent, we're supposed to reserve some secants if necessary, and convert the rest into secant. So do that now. Pause the video, use your knowledge of trig to change this into secant and see if that integral is doable. So if I do this, I'm going to end up with, I'll pull the 2 out front, 2 times the integral of secant squared u minus 1 du. And now I should be able to integrate this. Secant squared is actually just an integral that we can do. Remember that the derivative of tangent is secant squared. So this is 2 times tangent u minus u plus c. And in some sense, this is getting very close to our answer. The only issue is this needs to be written in terms of x. So how am I going to turn this thing back into x? Well, this is where our second video comes into play. The second video is about how to change things around. At the very beginning of this problem, we said that we were going to use the substitution x equals 2/3 secant u. Well, to me, what that means is it means that secant u is equal to 3x over 2. So what I'm going to ask you to do now is to take this statement and figure out what tangent is. So work through that, and then we'll come back together and finally finish this problem. So secant u means you've got a triangle. Angle u is here. Secant is 1 over cosine. So this 3x over 2 is hypotenuse over adjacent. So the hypotenuse is 3x, the adjacent is 2, and this missing side will be the square root of the hypotenuse squared, 9x squared, minus the other side squared, 4. And even right there, like, this should be feeling like magic to you. You're like, whoa, what a coincidence. There's a square root of 9x squared minus 4, which is totally what we started the problem with. This is a sign that things are going well and that we're doing things right. So let's finish the problem. I know we're anxious to get this done. I'm going to have 2 times the tangent of u. Tangent of u is opposite over adjacent. So 2 times the square root of 9x squared minus 4 all over 2 minus 2 times u. And what is u? Well, using this statement right here, we can see that u is basically arc secant of 3x over 2. So 2 inverse secant of 3x over 2 plus c. And because that's messy and I can cancel out these 2's, I want to write it again. My final answer looks to be the square root of 9x squared minus 4 minus 2 arc secant of 3x over 2 plus c. Now at the end of all of these other videos I've been saying, hey, this is an ugly problem. This is a really ugly problem. But we did it. But we have further expanded the limits of the things that we can do with integration. I do have one more example of these problems. I wanted to give you guys one more chance to look at them. So hang in there, we'll do one more and call it a night. I don't know if this problem's going to be better or worse, but I know that because we've gone through one of them, this one should go a little bit faster. If you're feeling up to it, try the whole problem by yourself and then check the answer. What you may find more helpful is to sort of work step by step and then watch minute by minute to make sure that you're getting them right as you go along. But definitely do as much of this as you can on your own so you can get a chance to see whether or not you know what's going on. So the first thing to do is to set up the substitution. Because it is constant minus variable, it's going to be a sine substitution. So I'm going to use x equals, and it's really interesting because there's no constant in front of x squared, and because there's a 1 here, you don't really need the coefficient. I'm just going to use x equals sine u. That means my dx is cosine u du. The next thing that we said after that was we usually simplified the thing that was in, like the binomial expression. So let's start with 1 minus x squared and see where it leads us. 1 minus, well, this will be 1 minus sine squared u, which is cosine squared u. So now we know that's what's supposed to go inside of that square root. So we bring everything back into this. We have the integral of x squared, which is now sine squared u, over the square root of cosine squared u times dx, which is cosine u du. And this is really neat because we know that this square root of cosine squared is going to become cosine, and that will divide out with the other cosine. So this integral ends up just being the integral of sine squared u du. Now this was one of our integrals from before. And actually, I just remembered something. It's very tempting here to plug x back in and go, oh, cool, that's just x squared, yay. Unfortunately, it would be x squared du, which is going to give you like dx over cosine u. Basically, it's going to turn it back into this. Once you've done this, you have to take this integral next. So I hope you guys remember how to do sine squared u. Definitely, work through that on your own. Practice that and then come back. So sine squared u, we accomplish that by doing power reduction. We do 1 minus cosine 2u over 2 du. So we can bring the 1/2 out front. 1/2 the integral of 1 minus cosine 2u du. So this integral ends up being 1/2 of u minus 1/2 sine 2u plus c. And then we know that we're going to need to change this back into x. And so anytime you've got a sine 2u like that, it makes sense to use the trig identity. We actually did a couple of those practice problems back then. So 1/2 u minus 1/2 times 2 sine u cosine u plus c. So these will cancel. Last thing I have to do now is put this back in terms of x. Remember that the substitution I originally used was x equals sine u. So that's good news, because it means we can plug in a few of these things right now. I mean, we know that this u in the front is going to be arc sine x. Then we've got minus sine u. I mean, that first sine u is just going to turn into x. The only thing I really need to work through is what the cosine is. So, we handle this like we've done the other things. We draw our triangle, angle u here. This x is really x over 1, so I have my opposite being x and my hypotenuse being 1. That means the adjacent side is the square root of 1 minus x squared. Again, we're totally not surprised because that was the expression we saw in the beginning of the problem. Last thing we do is we figure out what cosine u is. Cosine u is this over 1. So right here we get the square root of 1 minus x squared plus c. And instead of leaving this entire thing multicolored, we'll put the entire answer in green, just to represent how excited we are that this is done, or at least how excited you are to go and do different things now, because we finished this problem. Okay, I love these. There's just a sense of wow, this will work. This just feels like magic the whole way through. After 15 minutes of this, I don't know that you'll feel that way, but it's how I feel about it. So I look forward to seeing you guys in class tomorrow and having a huge smile on my face, and hopefully seeing at least one smile on one of yours. Have a good one.